The error so embarrassing that NASA almost didn't want to admit it, and that cost hundreds of millions of dollars on Mars. It didn't begin with a massive explosion. It didn't begin with a technological defect, nor with a dramatic system failure, nor with a lack of intelligence. It began with something so simple that for a while it seemed too embarrassing to be real. So simple that it became one of the most emblematic episodes in modern engineering. Only later would the exact bill arrive. Cold, implacable. $327 million, lost not because of a major mistake, but because of an invisible detail. Years of work, millions of dollars invested, some of the brightest minds on the planet, trusting that everything was under control. By the late 1990s, NASA was preparing for another decisive step in the exploration of Mars. This was not an experimental mission. It was not an improvised test. It was a carefully planned operation, designed to answer questions that had intrigued scientists for decades. The red planet had already shown clear signs that, in the past, it had abundant water. Dry riverbeds, carved valleys, minerals that only form in the presence of liquid water. The big question was, what happened to Mars' climate? To answer that, the Mars Climate Orbiter was launched, designed to become the first true weather satellite of another planet. It would study the atmosphere, map water vapor, dust, and temperature, and serve as a communications relay for future missions. Every stage had been planned with almost obsessive precision. Simulations reviewed countless times, protocols validated, software tested across thousands of scenarios. Data flowed normally. No parameter exceeded operational limits. No subsystem triggered contingency protocols. Readings remained within expected margins. From an engineering standpoint, the system was operating in nominal mode. For months, the spacecraft crossed deep space, while teams on Earth monitored every signal received. Small trajectory adjustments were made. Fine, routine corrections, almost invisible. Nothing suggested that anything was out of place. No critical anomaly was recorded. No telemetry indicated imminent failure. And that is exactly what makes this story so disturbing. Because the error wasn't in something broken. It wasn't in a defective component, nor in frozen software. It was hidden in something much smaller, much quieter. At some point in the process, two different teams were working with different measurement systems. One used the metric system, the other the imperial system. The numbers were correct within their own standards. The equations worked, but they were speaking different languages, and no one noticed. There was no alarm, no explicit warning. The data continued to look normal. Meanwhile, the spacecraft's trajectory began to drift slowly, millimeter by millimeter, calculation after calculation. An error too small to draw attention, but one that accumulated in silence. What's most unsettling is that there was no villain. There was no clear incompetence. There was trust. Each team assumed the other had checked certain details. Each system assumed the data had already been standardized. And when everyone trusts, fewer people double-check. As the spacecraft approached Mars, adjustments continued. Small thruster burns, nearly imperceptible corrections. Nothing that justified aborting the mission, until the most critical moment arrived. September 1999. After nearly 10 months traveling through deep space, the spacecraft approached Mars for orbital insertion. It was a maneuver with no margin for error. There was no plan B. Either it worked, or the mission ended there. The plan required the spacecraft to pass through the Martian atmosphere at an extremely specific altitude, high enough to avoid destruction, low enough to be captured by the planet's gravity, an invisible window in space, narrow, implacable. In control centers, engineers monitored the data in real time, speed within parameters, trajectories seemingly correct, no subsystem operating outside expected limits, no critical alerts, no technical reason to abort the sequence. And then finally, it entered the Martian atmosphere, but not at the planned altitude, not between 140 and 150 kilometers, much lower, around 57 kilometers. In space, that difference is not a detail, it's a sentence. Even with an extremely thin atmosphere, the velocity was far too high. Friction increased violently. Temperature rose in seconds. Aerodynamic pressure exceeded structural limits. Sensors began to fail. Data became unstable. The signal weakened, until suddenly, Silence. No final images, no emergency transmission, no chance of correction. The spacecraft simply disappeared. In the control room, engineers continued staring at the screens, waiting for the signal to return. Delays happen. Interference happens too. But minutes passed, then more, and the confirmation came slowly. The mission had been lost. The investigation began. Days of analysis, simulations redone, data reviewed line by line. And then the truth emerged. Too simple to seem real. The error was in the units of measurement. For months, thrust data had been interpreted as if it were in metric units, when in fact it was in imperial units. An error factor of approximately 4.45 times. Small on paper, gigantic in space. Each trajectory correction was calculated using distorted values, nothing large enough to trigger immediate alarms, but accumulated over time enough to destroy the mission. The impact didn't stop there. Months later, the sister mission, Mars Polar Lander, was also lost during its landing attempt. A different error, another silent failure. Another devastating blow in the same year. Mars reinforced its unforgiving reputation, the so-called graveyard of the solar system. Historically, nearly half of all missions sent to the planet have failed. Not due to lack of technology, but because Mars does not forgive assumptions. The response came years later, with a mission built on a new principle: extreme redundancy. The Mars Reconnaissance Orbiter. It did what the 1999 mission was meant to do. Studied the climate, mapped water, observed the atmosphere in extremely high resolution. And it does so to this day, serving as the primary communication bridge for robots on the Martian surface. The error was not forgotten. It was turned into a rule. Protocols were rewritten. Standardizations became mandatory. And any engineer gained the authority to halt processes in the face of inconsistencies. Because the true enemy was never Mars. It was assumption. And only then, near the end of this story, comes the final layer. And in the end, the technical truth was confirmed. The Mars Climate Orbiter never entered orbit. It disintegrated while crossing the Martian atmosphere, incinerated by friction, leaving no recoverable debris, no final images, and no chance of correction. The mission didn't fail in silence. It simply ceased to exist. There were no astronauts on board. No human lives were lost. And yet, the impact was enormous. $327 million. Years of scientific research. Knowledge that can never be recovered. All lost because of an invisible detail. If you enjoy stories about invisible failures, domino effects, and small mistakes that change the course of history, like the video, share it, and subscribe to the channel. The next video is already waiting for you. Another complex system, another overlooked detail. In history, the world doesn't change only because of great decisions. Sometimes, a forgotten detail changes everything.